I've already done. I've probably done.
Fine, we can do three now. Yeah.
Draw next to draw.
Fine, we're gonna go back to trees now. So that's it. We can copy it out. Okay, guys, that's four. Thank you, thank you. And we focus, please. Okay, a path is a route between two vertices so that no edge is used more than once, right? Not all edges need to be used, and the starting point is not usually the end point. Okay, we said that. Then we looked at this graph on the side here, and I said, let's find a path from vertex A to vertex B. Do you guys remember that? Maybe if you didn't get a chance to copy this down, you can copy this down now. It's nice to actually have a diagram that indicates these things instead of just words. What? Why? No, it's fine. If it works for you, keep going. I was just a bit taken aback. Okay, guys, so we said no, why? Fine. We said one half from A to B would be if you're going from A to B, and then from B to C, and then from C to D. Right? That would work. That would get you from A to B. Then we said another one is let's go by a bit of a roundabout way. Let's go A to B, then B to E, E to C, and then C to D. Right? But guys, we can also go from A to E, and then from E to D. That would be the shortest path. Right? There were lots of others as well. You could also go A to B, B to E, and then E to D, alright? There are lots of different paths. Basically, a path is just a route to get you from one vertex, to another vertex, and you may not use the same end more than once. And that's the important thing, okay? Shortest path, yeah, we are getting because there's like 1,000 paths. So good. Yeah, you go. Alright, are we fine with path, guys? Now the second one. We're looking at the next one. This is important, guys. Now we must remember the definition of a path. And now we're specifying that definition a little bit more. Now we're saying a path that starts and ends at the same vertex is a closed path or circuit. Okay, so a path, oh, that's too big. Path that starts and ends at the same vertex is known as a closed path, or we usually use the word circuit. So path, right, is a route from one vertex to another one, not using the same edge more than once. But now, guys, if you go back to the original starting point, then it's no longer a path, then it's a circuit. Okay. And if you're thinking in terms of like when you're running, if you're doing a circuit, you're starting at one point and you're going kind of in a loop and you get back to the starting point. And now I'm not going to lie to you, the itinerary, I've never seen that used in graph theory, but what they're saying there is starting at a different vertex and following the same path does not constitute a new circuit, because it's just a different version of that circuit, but they're using the term, I'm going to use that word in graph theory, but I mean, yeah. You can highlight that one.
I mean, it's fun on the rest of the graph where is one and then explain what makes it.
we are, so that's why we're all kind of jumping around. So guys, if we're doing this now, I don't know if you want to draw the same picture again, just underneath your circuit one, Yes, but it is, but a part is not necessarily circular. Yeah. Just if you have the same focus. So I'm going to show you now. I'm going from A back to A back. But now they're saying it's going from B back to B, following the same circuit. But it's just a different version. Oh, here we go. Okay, I'm just going to show you that picture again. I'm going to actually erase all the stuff that I wrote here. Are we fine? Can I do that? Now guys, if they say in a question that you're doing a circuit from vertex A, they're not going to tell you to vertex A. You have to know that a circuit starts at the same point as vertex, right? Circuit has the same start point and end point, right? Because I'm listening to multiple conversations at the same time. All right, so there we go. That would be an example of a circuit, right? Importantly, guys, you can't use the same edge more than once. So you're starting at A, you have to go all the way back to A, but you can't use the same edge more than once. All right, there could be other options for circuits here. We can also do A to B, then what about B to E? And then, look at that. That's a circuit, right? They didn't say it has to go via all of those edges. The circuit just has to go from A back to A. All right, so that works. A to B, B to E. Okay, that's also a circuit. All right. Then what about A to? You can also go the other direction. Hey, you can do A to E, and then maybe E to C, and then C to B. Now, guys, if I now do this, am I allowed to? Would that be able to get me back to point A? Because I've already used that edge, hey? You're not allowed to use the same edge more than once. So I wouldn't be able to do that, but I can go from B to A like that. Okay. No, stop it. No. Okay, now we can go back to tree, finally, because we've now discussed what a circuit is. Guys, a tree is a connected graph with not a single circuit in that whole graph. Let's take a look. If we're looking at graph C, the graph C is a tree, right? If I am here, is there a circuit? Is there a way of going via some of the edges that I have to get me back to that, I want to say point, back to that vertex without using the same edge more than once? Okay, if I do this, now I can't go back, right? Now I can't form a circuit. Because if I go back, I'm going to use the same edge again. Right? Does that make sense? What about the other one? What about this one here? Can I form a circuit if I go down here? Let's look at that one. Is it a way for me to get back to that vertex without using this edge again? I can do that and I can go up there. Or I can do that and I can go up there. Right? So there are circuits in this graph. What about graph B? If I start here, is there a way for me to get back to that vertex if I go there and then there? Right? Now guys, graph B is a bit weird because there's this part here, okay? So this wouldn't be a circuit in this section of the graph, but because there is a circuit in this section of the graph, it's not a tree. Okay, it's only a tree if it has no circuits in the whole graph.
The second part, which is just the line, is on its own reflection.
Yeah.
Just the line.
So just if it was just the line, that is a tree.
It's like
Yeah. Yes, it is. Yeah. But as soon as I do this, now it's no longer a tree. Guys, can you focus? Where am I looking now? Am I looking at this one here? At the bottom, okay? A, B.
In the top there, A, B, B.
Mhm.
Is B, A, B, A, an itinerary of A, B, B, A. So I keep it a very itinerary of
It's just basically a different version of it. Okay, what comes after tree? Undirected graph. No, first let's do weight. Yeah, I'm just waiting.
Yeah.
I was like, just waiting.
Why would they?
It's weight for weight.
Why would they do
That is that a different kind of graph? It's weight to graph.
No, we're the left.
No, well, it is, but can you get into it?
it. Feels like it's in the last.
I think many people would disagree with you on that.
I said actually. I'm not gonna lie.
Have fun, eh?
Yeah.
Alright, so wait. Am I being sarcastic? I guess you'll never know. Okay, wait. Absolutely.
Well, better is the grade.
Oh, wait, doing a paper class.
Well, better is the grade.
Obviously, a wolf is in her grade class. Alright, the weight of an edge. The weight of an edge. So guys, don't write undirected graph. Please write weight first. Again, they're using a different. They're using a different. I haven't even. You're kidding. No, it's a weight. It's a thing. Oh no. Alright, guys, the weight of an edge is the distance, time, cost, or any other factors tried with. Basically, you'll get graphs with numbers written next to an edge. Okay, and each number is going to represent something. Often it's distance, right? So if I give you a question like, for example, you have to deliver newspapers or whatever, and you need to cover all the streets in this area, but you want to, or let me rather say it like this, you want to go from school and you want to cover a certain amount of streets and get back to school, but you want to do it in the, you don't want to cover a lot of distance. So what would the shortest route be? All right, that kind of thing. So then you would actually look at the weights, the actual values that are on each edge, and you would find the shortest one. Okay, you're not going to sit there with a ruler and going to measure the actual distance of the line. That's not what's going to happen. It's almost like we're going to give you like a map kind of situation, right? Does that make sense? You'll see when we get to it. Distance, time, or cost ascribed to it. It's usually distance or cost. I've seen questions about like airlines as well, where you're taking different flights and with different airlines, different flights. No, but yeah, the weight is just the value that it's ascribed to that. Yeah.
Someone's car is like short.
I've been experiencing the whole time. Okay, now we can do undirected graph.
Hey, oh my gosh, is that a neat one?
So guys, undirected graph. And we are going to work with only undirected graphs. We don't work with directed graphs. What that means is if I'm walking from school to my house, it's a certain distance. From my house back to school is the same distance. Right? Does that make sense? But in terms of directed graphs, sometimes if you fly from Cape Town to Joburg, you're going to pay a certain price. But if you fly from Joburg to Cape Town, it might be a different price. Right? So that would be a directed graph scenario. That's not an infinite. Exactly. All right. We're going to work with the same weight from one vertex to another vertex, and from that second vertex back to the first one. Okay, that's an undirected graph. Can we click? Yeah.
If you have, for example, a loop, right, with just two vertices, and then they have the same weight, is it split directly graph?
The box. What did they say neighbor?
They
If
said
a group or multiple ages present, the graph is then directly.
That's
You're
what-
saying if it has the same
they
one.
have to say, wait, then
Hmm,
A to B is equal to
yes. I'm not sure. I think they won't text you on that.
Yeah.
Well, yeah. All right, we're almost done for the day. Order the graph.
What is the mom?
Okay, order the graph, number of vertices in the graph. Very easy. You just count the number of vertices, that is the order. So guys, I'm not going to ask you what is the number of vertices. I'm going to ask you what is the order, and you must know what order means. Right? So guys, it's an easy section, but it is going to require you to actually memorize a whole bunch of terms, which I think you might not be too happy about. But if you do that, you can get good marks quite easily for this section. So if we're looking at this graph, how many vertices are there? 1, 2, 3, 4, 5. So the order of this graph is just 5, right? Just the number 5. How many vertices are there? 5. Then the degree of a vertex, not the degree of a graph now, the degree of a vertex is the number of edges that are connected to that vertex. Right? Oh, yeah. So I would like you just to copy this graph again. And we are just going to write the degree of each vertex just next to it. Okay, so you just draw that graph with me. It doesn't have to look exactly like that. Check that you have your ABC and they have the edges between them, at least. But if it looks a bit wonky, that's fine. Please, no. That's like I'm going to go Are you able Perfect.
That's the story.
The other one.
It's the one behind. I mean, that one behind.
One behind that.
No, that one's safe.
No, both of them. There we go.
Thank you.
Okay, are you guys done? No. I wonder why, actually. Okay, next to A. How many edges are attached to this vertex? Or connected to it? 2. So the degree of vertex A, that's fine, that's fine. The degree of vertex A is 2. What about B? 1, oopsie. 1, 2, 3. The degree of vertex B is 3. C, also 3, hey? D, 2. The number of the number of edges connected to vertex B is 2. And then for E, do we see that it's 4? 1, 2, 3, 4. Alright, the degree of E is 4. But the order of that graph is 5. Okay, it's easy to get confused, right?
Now, is this a simple?
Wait,
Don't see enough. We get comments.
multiple edges. Yeah.
You say A has a degree of, or is it?
That's really very exactly.
No, I'm trying to ask.
No. All right, regular graph. There we go. We're almost done with all the terminology, guys. I feel like you're gonna go home today and say to us, but I want to quit the I'll pass you guys on to the sport next year.
No.
That's it, Jay.
I've never had this.
You know, like this.
That is the reason.
Yeah, we want to keep not what I'm saying actually. I'm just saying, oh, she's the other AP teacher, that's why I'm.
When you say, man, kick them out, people out, and then they say, yeah, I think you're practically kicking them out.
Really not, no, actually.
Say you will stay here.
You, even if you're
Why do you look at me?
Okay. Alright. I'm not allowed to drop the subject in. Okay, guys, a regular graph has all vertices of the same degree. Thank you. So that means every single vertex has the same degree, right? So if we're looking at graph D, is that the case for graph D? I'll go back up to the terminology now. These vertices do not all have the same degree, right? So this is not a regular graph.
With every polygon.
Surely. Surely it would be. Yeah. Well, anything with outlines going in between.
Yes.
Okay. I don't think that's a term. I think they'll just ask you, is it regular, yes or no? So guys, let's quickly draw an example of a regular graph. If we have the same shapes that we had for that previous one, if we do a 1, 2, 3, 4, 5 situation. Three, what do you mean? I don't know what the shapes. So you see mine even looks a bit wonky. It doesn't really matter. Oh, sorry, you can't even see that. My apologies. Okay. C, D, E.
That's straight line.
I just love the fact that some of you have been talking a whole hour and I'm gonna clap you guys with the terminology. I think you failed.
Yeah.
Mm-hmm.
It's only polygon in straight line.
We're on to that section.
Everything is still written.
Yes, it is. Everyone's here. Like parent teacher meetings. Pull up with name I mentioned the most. Yeah, Sandra. Okay, last one. Are we fine, guys? Regular graph. Oh, actually, I didn't need to look at that. Yes. Sure. Okay, the size of the graph. Yes, Jonathan.
Can a non graph is not connected, right?
What do you think? A graph is not connected. Then why are you asking? Yes. Wait, what? We can do some identification. See if we can draw what do you up it and not? If it's not connected graph.
Straight line.
That's not. No, because then they won't. They won't. No, I'll have to go. All right, so thank you. Thank you. Can't be. All right. Adjacent vertices are directly connected to each other. Then we call them adjacent vertices. So if they join by a common edge, we call them adjacent. I think that's quite self-explanatory, right? It's two vertices that are, but they can't just lie next to each other. They have to be connected to each other as well. Okay. So it can't just be one vertex, another vertex. Oh, they're next to each other, so they're adjacent. They have to be connected as well. Okay, almost there. The neighborhood of a vertex are all of the vertices that are directly connected to that specific one. So I'll show you an example now. Directly connected, not indirectly. Remember last time we spoke about the difference between directly connected and indirectly connected. Okay, so they are saying vertex C. I'll come back to the words just now, guys, but for vertex C, which other vertices are directly connected to this vertex? B, E, and B.
Okay.
All right, so the vertex, the neighborhood of vertex C would be B, D, and E. Okay, so then you'll literally list the vertices. Okay, we're looking, I have 2 more terms to go over. And then one little thing, and then we can actually start doing work with graphs next time, not just terminology. Maybe we have to start so complex. Maybe
There's nothing wrong with it.
clean up distractions.
There's a reason she's called corruption.
Yes, absolutely.
Put you on a time.
I know, thank you. You have told me.
Yeah.
All right, the girth of a circuit is the sum of the weight of its edges. It doesn't have to be a circuit necessarily, it can actually be edge graph. I'm not sure why they chose to use the word circuit there. Because in this particular word, edge graph. All right, the girth, there we go. We can add all the edges weights together. That is the girth of the graph. Last one, planar graphs. We are going to practice working with planar graphs next time. They can be drawn without edges crossing each other. Don't worry about that. I'll show you when we do it. It's a bit complicated to explain if you don't have actual examples. Okay.
After Jake, but
Yes. And then, guys, the last thing, just write this down very quickly. We are also going to discuss this next time. So next time, we're doing planar graphs, and we're going to talk about the number of edges in a graph. So they're saying that in any graph, the number of edges is half the sum of the degrees of the vertex. Okay, so we're gonna do some investigation next time just to see why that is. All right, but just write it down for now. Actually, there's no way you're.
No, you can't take photos.
No, write it down. No.
nice, you know how to take some.
Oh, I do. Oh, whoa.
So every edge will have to be next to first. So there'll be, yeah.
And that's it. And last thing, and then I'll put a bracket. Okay, great.